So today I'm going to talk about the status of my build, Wonderful Wandering Growth, and I'm going to talk a little bit about hobbyists. So what I want to talk about hobbyists. One, I want to talk a little bit about the characterization, what is a hobbyist? I want to talk about how we can help such a hobbyist. And I'm also going to talk a little bit about the specification for a Mars garden. We'll start with a recap of the last presentation I made. I talked about next steps. Everything in gray, there's been no progress. The things in black, so let's talk about them. First, I wanted to port my software to somebody else's rover. In fact, we're doing a reverse port. Victor's container-based software, we're trying to port it to my rover. And there's a slight problem. He prefers a 64-bit operating system, and I have a 32-bit operating system, which is apparently the standard for Raspberry Pi. There was the issue of changing the execution architecture. So I'm fighting it. I know it will have to be done one day. I'm fighting it. But already the problems I had with buses, which I'll talk about in a minute, have been causing changes. And last, collaboration between rovers. One of the reasons for installing Victor software, if you recall, Victor has a VPN which allows the rovers to share a network. So after we manage to install it, we're going to try to do some sort of collaboration. I'm not sure what. So in the status, I'm going to talk about what the system actually looks like. There's going to be some repetition of previous, but I'm going to describe the entire system. I'm going to mention some particular problems that I dealt with, and I'm going to give you two short stories about rabbit holes I fell in and still am stuck in. Okay. So here is a diagram showing all of the components of the system. For obvious reasons, they don't have any lines connecting things together. What you have on the left are the software components, and on the right, you have the hardware components. Everything below TBD are things that have not yet been done at all, but we are expected to have them. And let's walk through it. First, we have some type of web server or web page which allows access to the robot. At the top level, the various interfaces to the outside world. There's a Discord interface for giving commands and getting feedback on Discord. There's a Twitter interface for giving commands on Twitter and getting feedback. Right now, it only gives feedback on Twitter. And there's a Twilio interface for sending video out from the robot on the internet, but it could also be used for sending video and other types of data into the rover. As a layer under that, we have command wrappers, meaning when you give a command in Discord, it is wrapped up in a wrapper and sent for execution. And both Discord and Twitter and also Twilio will use some type of command wrapper. What is wrapped up in the command wrapper are particular action scripts. So I have one action script for moving the camera. I have one action script for moving the bot. I have additional user configurable action scripts. And whenever you execute one of them, you give the command through Discord, it gets wrapped up, and then it gets executed. In parallel with the action scripts, we have a video streamer program, which packages up the video using headless Chrome and sends it out through Twilio. And we also have a logging system. The logging system generates a state vector right now about once a second, showing the state of multiple sensors on the robot, and also including an image. It acquires an image, so we can see whatever it is a robot's looking at. The layer below that, there's a camera interface, because we're not using standard Raspberry Pi camera, and there's a servo interface. Again, we're talking software, and I'm putting a little star next to it because it's still a work in progress. Basically, the servo interface takes low-level commands and passes them on to the hardware on the right. Just to give you a feeling of software components that have not been created yet, the various watchdogs to make sure the robot isn't doing anything dangerous, autonomy functions for the robot to walk by itself, low-level computer vision for processing the image and generating, I don't know, stereo depth, object recognition, and so on. A sharing system to support actual sharing between multiple users. Right now, multiple users can access the interface, but the robot itself is not managing the sharing between them. A cooperation component, which, like I said, something to do with what Victor Hill has on his VPN. A location system, which defines the location of the robot. Basically working on defining what that even means with Eric. The sets of novel gates, feedback loops, and what I call perceptozoids. Perceptozoids are little pieces of software which takes the raw sensor data and turn it into a feature which is somewhat more high level and meaningful. I'll perhaps give you an example from computer vision. It takes a stream of video and tells you what direction the robot is moving based on the optical flow. Okay, so these are things which will be done. And now let's talk about the hardware. So we have a power board, which includes a battery, charging circuit, and the voltage provider, both for the motors and for the CPU. By the way, everything on the right comes from the manufacturer. Okay, it's a pre-made device. On the left, everything I installed except for the servo interface, which, like I said, is now being rewritten. So, getting back to hardware components, so there's a power board. There's some sort of interface for connecting various peripherals. There's a particular section for providing power and serial commands to the smart servos, which control the robot. This is a legged robot. It has 6 legs. Each leg has 3 smart servos. So we have altogether 18 smart servos. We have an ultrasound rangefinder. We have 2 plane servos, which control the camera. We have a 6 degree of freedom sensor, which gives us the acceleration and rotation. And it also gives us a temperature, but not using that. We have 6 legs, a body, a camera mounted on a head, and the ability to add various add-ons in USB. In fact, maybe the right thing to do is to show it. Okay. So this is the robot, 6 legs, camera. I put on some sunglasses. Inside, you can see the battery, the Raspberry Pi, and above it, a dedicated hardware board. Okay. So I also have, if you notice, a servo bus controller with a big red X in it. That's a very sad story. Basically, the rover has the hardware for controlling the servo bus, and it's inoperative. And I'll tell you about that in a minute. But what it means is that where you would expect hardware control of all of this hardware, you actually have software control of all of the software, all of the hardware. So if you think about the architecture, you have software, you have smart servos, which mean each one has its own little CPU and it can process commands and so on. And you would expect to have an intermediate controller which gets software commands and then controls the smart servos in real time. And that is this component. And that component is absent. And we're trying to figure out if we can bring it back. One of the things I'm working on with Eric, I'll call it mid-level hardware. That's hardware which does integration of sensor data and commands and does something interesting to it, conceptualizes it, but it's, you know, still a work in progress. And sensors, we haven't added any, but Venkatesh, you said you were planning on having lots and lots of sensors. So maybe I'll just do a few of them, but still we'll have to add more sensors. The hardware already supports a USB, and it supports a I2C bus, actually more than one of them. So there's no mechanical problem of adding sensors. Any questions about this architecture? No. Okay.
What is a smart servo?
What is a
Smart servo on the right column?
Okay. Servo motors have a motor and they have gears and they move to positions that you tell them to move to. And a lot of them also, well, some of them include an optical sensor, some other sensor that allows you to know what positions they're at. The smart servo includes a microprocessor. So first of all, you send it digital commands and it sends back digital responses. And second, it can give you useful information. So for example, you can give it a command, move to this angle at that speed. And that's it. The built-in microprocessor will move it to that angle at that speed. You don't have to talk to it anymore. And you can give it a command, tell me what is your temperature. You know, servos heat up, and when they overheat, they burn out. So you can tell it, what is your temperature? It will tell you what is its temperature. You can give it a cutoff temperature, so that when it reaches that cutoff temperature, it will stop working. You can get the voltage. The voltage is an indicator of, you know, how well it's working and what your battery status is and whether you're asking too much of the system. So basically, it's a servo which has a little bit of brains, and these little bit of brains allow it to be more autonomous and state aware, or at least help you become state aware.
So you have already used the servos on the rover are already these servos?
No.
Okay.
The 18 servos which control the legs are this type of servo. The 2 servos which control the camera head are not. So I can take the rover now, and there's other things like drift correction and calibration, whatever you might expect in such a servo. Think of the following. If I have a servo, I can have it tell me what angle it's at. But servos for the camera, you can't do it. The servos for the camera, you have to maintain their position in software. You can't ask them what direction is the camera pointed at. And of course, they're much cheaper and much smaller and lower power. Now, most servos that you buy, especially if you build them yourself from a motor and a gearbox, are plain servos. But there's definitely working with the smart servos is much nicer than a plain servo. And in fact, I keep on saying, well, I wish it had this function, I wish it had that function. Okay, you get addicted to having each motor being able to tell you what's going on and act semi-autonomously, because you give it a command and it carries it out. Let me give you an example where it's not as useful. Let's say you want to have the servo move until it feels resistance, and when it feels resistance, you know it touched the ground and it should stop moving. So if you have a plain servo, you have to have a sensor which tells you that it stopped moving. If you have a smart servo, you have a sensor inside, you can continuously ask the servo, what position are you at? And when it tells you that it's not able to move anymore, you know that it touched the ground. If it was an even smarter servo, you'd be able to close the loop in the motor itself. And that we can't do. Okay, if you think about wheels, so think about slippage. If you have two wheels and you want to distribute power, and if one of the wheels is slipping, you want to reduce the amount of power you give it. If you're doing it with a plain servo motor, you have to continuously track the actual speed of rotation of each wheel. And when one of the wheels starts rotating faster, you have to lower the speed. But if you have a smart servo, smarter than the one I have, you can do it by itself. Any other questions about the system? Oh, by the way, just to give a feeling, the smart servos, when you buy them separately, are $15 to $20 each. So if you look at the total price of the robot, it's basically a way of selling you servos at a discount. Okay, there's 18 of them, and each one of them is, let's say, $20. So that's already the price of the robot. Okay, so what are the problems I've had to deal with? And when I talk about problems, I mean problems that prevented me or interfered with me exploring what I can do with the rover. So the first problem is that I don't have 24/7 power, meaning I can't keep the rover on all the time. And unlike a Roomba, it doesn't know how to charge itself. There's too much happening at the software level. I need better support for the hardware. I'm always running out of resources. You know, I wish I had more RAM, more CPU, faster response times, more disk. There's a general problem of wear. Okay, I've had one screw fall out, but you can also see a few signs of wear on the robot itself. And there's always a danger of overheating. When it overheats, you can lose one of the components. But all of these problems are mundane problems. You'd expect them in any project. None of these are problems which really prevent me from doing what I want. They're just constraints. The more problematic thing is that there's too many windows, as in places I can go, and I don't have enough rocks to sort all of them. Okay, rover is a very complicated thing, and when you want to move forward, you have to move forward on multiple fronts simultaneously, and it's difficult when you have such a complicated device. So it's a situation more than a problem. Okay, so let me tell you first about a mini rabbit hole I fell in with Twitter, and I just jumped out before digging all the way to the bottom. So the general idea is we want to be able to control the rover by Twitter, and we want the rover to report what it's doing also by Twitter. So there's obvious problems like which videos to send and what form should the commands have. But it turns out there are less obvious problems that stem from the fact that Twitter was really not meant for this type of task. And one problem is that repeating tweets are blocked. You know, it goes in both ways. If you give the rover a command, go forward 2, and then a minute later give it another command, go forward 2, from Twitter's perspective, it's not a command, it's a status change. But you didn't change your status. It's the same as it was before, go forward 2. So it doesn't send the second command. Okay, Twitter has a mechanism for blocking repeated commands. And of course, when the rover reports what it's doing, again, repeated tweets are blocked, which means if you just show a picture, here I am, and then another picture, here I am, it blocks one of them. It looks only at the text, it doesn't look at the pictures. So when the rover's doing it, it's easy to modify the text in such a way that it overcomes Twitter's algorithm. But how to do it for humans is not so clear. I think obviously if you do a direct message, we don't have this problem. But the goal when using Twitter is to work in public. So we want people to send the message everywhere and not just do a DM. I decided to ignore this problem for now because logging became more important. Now, the second thing which happens has to do with cycle time. You give a command, the command takes a few seconds to get to the rover and a few seconds to happen and a few seconds to be reported and for you to see it. And while this loop is happening, okay, it's really a type of mini OODA loop, somebody else sends the rover a command. Okay, the rover is not exclusive. So it's not clear, and all of these commands appear in the stream, and it's not completely clear how do we show this in a way that people can understand it and not make a total mess of what the robot's doing. Left, right, left, right, left, right, and things like that. So Twitter has all sorts of special features which are not exactly compatible, but we will prevail. I'm not worried. But like I said, I got out of this because my work with Eric requires us to focus on logging. Okay, logging basically means, as I said before, every so often we generate a vector of everything that the rover is doing. And in the most basic level, the vector includes the positions of the 18 servos, a picture, the angles the camera is looking at, the range that the ultrasonic rangefinder measures, the acceleration information, and sensor data in general. So If you remember, a very simple architecture, we just add a logging system here. And the logging system talks to the servo interface and the other items, and everything's hunky-dory. So this is what it looks like. You have one command running. The command talks to the servo lib. You have a second command running. It has its own copy of the servo lib. And you have the logger running, and it has its own copy of the servo lib. And each one of the libs talks to the servos using their serial connection. So this one says move forward, and certain motors get commands. This one says rotate camera, and the camera gets commands. And this one says tell me where you are, and they tell it where they are. Okay, so that's wonderful, and does not work. Turns out that doing the logging interferes with carrying out the commands. What happens is that movements go missing. The movements that you have are very jerky, don't get all the logging data you should have. So somehow, this isn't working the way it should. Okay, so it seems like some sort of bus clash, but it's strange because there's a dedicated bus controller board. But when I dug into it, it seems that the software, and when I say all the software, I mean there's multiple different variants of programs that they have there and servo control libraries. They all directly control the servos, smart servos, and they bypass the board. Now, besides being a problem, there's another issue. We couldn't figure out, and remember we have a board. What does a board do? In an ideal world, you tell the board, execute action group number 5. And action group number 5 means at time number 1, move all of these motors to this position. At time number 2, move all of these motors to that position. At time number 3, move all of them to that position. And if you repeat that, you can get, for example, a walking gait. That is what the board should do. Now, these action groups are important because, as you might recall from a few presentations ago, in order to walk outside in the garden, you have to define special action groups that lift up the leg high. While in order to walk inside the house, you don't want to lift up the leg high because you don't want to have too much slipping motion on the floor. So there's another problem which is not solved yet, which is how do we load new gates onto the bus, the dedicated bus controller board. So the software seems to control the servos directly, bypassing the board. But the same robot is sold in an Arduino version. And in the Arduino version, the board is doing all of the controlling because there is no Raspberry Pi and there is no software. So, as I said, the natural thing to do is to have hardware controlling hardware. So we called up support. And we waited, and we waited, and we waited, and Eric contacted them, and they're supposed to be his friends. And he waited, and he waited, and he waited. So we did something else. Now, the servos, okay, all 18 of them sit on one bus. Okay, I'm calling it a bus because from a data perspective, it's one bus. From a power perspective, it's 6 separate buses. In any case, they have a packet format that includes a servo ID as part of the packet. So when you send a command to a servo, you say servo number 5 please rotate to position 22 at speed 23. And when you send the command, servo number 5, tell me your position, servo number 5 sends back a packet saying, servo number 5 position is 250. So this is an important piece of information. And then we started digging into the schematics.
The bus is I2C based, or what kind of bus is that?
Yes,
It is I2C.
no, yes, we'll talk about what kind of bus it is.
Okay.
It's a variant of RS-232.
Okay, so it's a UART.
Just a second. The Raspberry Pi has 40 pins going out. Multiple sets of these pins can be configured to act as serial ports. You have to enable them in software. The board has a UART, and if it were actually working, it would have to be able to work at 2 separate speeds. 192,000 baud, that's for talking direct, 115,000 baud, that's for talking directly to the servos, and 9,600 baud, that's for talking to the board. So the first thing I did was I tried to activate additional ports on the Raspberry Pi, hoping that the board was set up to listen for one connection on one set of pins and for another connection on another set of pins. The short answer is no, that didn't work. Suddenly I get an answer from support. Well, there were a few cycles, try this software, try that software, no, yes, no, yes. And then they said, look, here's a piece of software we cooked up. It works for us. And it's wonderful software, and it should work for us too, except that it doesn't. And then they say, so sorry, there is no access to the board in our model. Okay, remember I talked about the Arduino robot. In the Arduino robot, you connect the board by USB to your computer and download whatever it is you want to download. But you can't do it with the board that sits on the Raspberry Pi. It doesn't have that type of connector, at least not that we know of. And no, it doesn't work. So we definitely have to do a workaround. So the first question I asked, what exactly is clashing? Are the servos clashing, or is the bus clashing? In other words, could it be that when the servos get a command in the middle of working, they get confused? Now, why is it not a trivial answer? Because the software which controls the servos is works using delays. It sends a command, then it has a delay. So it could be that servos are not capable of working if they don't have this delay. And that's why you don't have clashes when the robot is working regularly. But if I give commands which overlap in time, it would do that. So I ran an experiment, and it turns out that the servos do not mind getting commands while they're working. And they're quite capable of responding to the commands. Okay, I had it move one of the legs up and down. And then I started shooting commands to all the other motors, and there were no problems at all. But the problem is the logging. Why? The bus is half duplex. So you have to tell the bus whether it's in read mode or in write mode. And you switch it from one to the other. So imagine that you start sending a write command, and simultaneously, or in the middle of it, you send a read command. The problem is not that the command gets lost. The problem is that the bus suddenly goes into read mode, and therefore none of the servos can hear the rest of the command. And as you'll see later, read commands are much, much slower than write commands. So it's very easy for the bus to be in a read mode when a different piece of software wants to send a write mode. So I built a semaphore, okay, between the servo lib and the actual control of the servos. And because it's Python, it's really easy to do. And basically what the semaphore does is it wraps up each atomic command inside each command, makes it atomic by preventing access to the bus by any other library until that particular atomic command executed. So if you send a write command, it waits until that command is finished before it releases the bus for the next command, read or write, to be sent. Okay, so this solves the problem. If I log, the logging doesn't interfere with the robot moving. From time to time, you have a hiccup when the bus is locked and it wants to send a write command, but that's just a delay of a few milliseconds, so no problem, no commands lost, no data lost. Now we can start seeing what's actually happening inside. Turns out that getting a simple data vector takes between 1 and 4 seconds. So reading an image takes 1 second. That's a problem that I'm ignoring for now, because you can also do it in parallel. But a single servo read cycle takes 42 milliseconds. Okay, so I did profiling on the software, and it tells me how much time is spent in each function and the average and total and so on. Asking a single servo, what is its status, takes 42 milliseconds. Now, just for comparison, if I had the servo board, I could give a single command, tell me the position of all of the servos, and it would manage that. So why is it taking so long? So the answer is they have a very unique way of polling the servos. You send a write command, which is tell me your position. Then you switch to a read mode, and you start listening on the bus to get an answer. And that takes 41 milliseconds out of these 42 milliseconds. Now, on the internet, it says that the servos respond so quickly that it's not even possible in software to switch the bus fast enough, that you have to build a little dedicated piece of hardware to do it. Now, what that means is that it looks like the board is doing some type of buffering, which is good because we like buffering, but it's bad because we have no control over it, and now we're waiting 42 milliseconds to get an answer to a stupid question. So what I'm going to do is I'm going to test the interlacing. I didn't do it yet. And then we'll also discover if the servos are smart enough not to clash with each other when they send data on the bus. In other words, obviously, when I send a command on the bus, it can only go out once. But if you have two servos trying to report their position at the same time, the question is, do they wait for each other or not? And maybe we will get an answer from the support. Okay, so just to be clear, this is not a problem that should be happening at all. But what is the alternatives? So there were all sorts of issues that I've been pondering all through the process, and the first one is buy or build. So let's talk about this issue of the servo bus. Using existing components is great. What was the alternative? We could have built the hardware, and Eric's been making noises about building the hardware. Okay, but that takes a long time to build the hardware and configure it and debug it and so on. Or I can take what I have, and some things don't work together, and we have to work around it. I have to choose between the problems. Even when you buy things, you can't avoid the complexity. The system is simply complex. There's no way of avoiding that. Building is slow, and what wins it over for me is starting at zero. So some of you are building your robot from the bottom up. Some of you are designing it as well. That is a very, very slow start. I'm like gratification, and waiting weeks before my robot takes the first step is just not for me. And also, when you buy something, you have the option of taking a big step all at once and having a big change in what's happening. I like that. Of course, you lose control and you have rabbit holes like the ones I just discussed. And the second question is, what's better, legs or wheels? Well, wheels are simpler, they're easier to control, they're much more reliable, and they're very efficient. Legs, on the other hand, are fun and they're cool. Having legs moving around is much more interesting than, wheels turning. They're multifunctional. You can do things with legs you can't do with wheels, like pushing, digging, lifting up, prying open. They have more interesting algorithms because they have this multifunctionality. And what I think is important is every robot has a mechanical structure which has intelligence in the structure itself. The structure is designed so the robot won't tip over, for example. When you use legs, you have a lot of the smarts is not in the leg design, but in how you control the legs. When you build a wheel, you can build a very, very smart wheel. But once you've done that, the scope of doing things with it is limited. Okay, so I would say that in a wheeled robot, more of the intelligence is found in the design itself, while in a legged robot, more of the intelligence is found in the control. And I like that. If I were building a real system, I would probably prefer more of the intelligence to be in the design and not in the control. But it's not a real system.
There is one thing missing. It's using rotors to fly around.
Yeah. Okay, any questions about the build?
There were a couple of slides there. You were referring to the board, and I wasn't quite sure which component is the board.
Okay, so I am actually missing the CPU board here in this drawing. If you're familiar with the Raspberry Pi architecture, you have a general purpose Raspberry Pi board, and then it's traditional to add capability to it by putting a hat on it. The board, the servo bus control board, is a hat provided by the robot manufacturer, which fits on top of the Raspberry Pi and provides an interface to peripherals, power and serial connection to the motors. You know, we talked about that the motors need a lot of power, and they also need some type of real-time control. It gives you support for the rangefinder, degrees of freedom, and all these other components. So there's a hardware board which controls all of these things. This hardware board also includes a processor and memory, and it has the capability, as advertised, of actually carrying out various mid-level functions like gates. They call it action groups, but it can even be more sophisticated than that. I once had a dream that I would be able to close a sensor loop through that board, meaning I would measure contact with the ground, for example, and the servo board and not the Raspberry Pi would be able to detect that measurement and change a command. I've given up on that dream. But, you know, okay, so that's the board I'm talking about. And yes, this slide, and I'm going to fix it, has a CPU board as well.
Got it. So as working right now, there is some sort of serial communication between the Pi and the servo bus control, but it's at a low direct level as opposed to higher level. It's on a per servo.
Yes, but I would say it differently. The servos have a low-level control. When you communicate with the bus, instead of the bus board, instead of giving the bus board commands, the only thing you can do is a pass-through directly to the servos.
I see.
But it's not exactly a pass-through because it appears to include some type of buffering. It's not clear if it does or could include full duplex. According to the software, it doesn't mean that it can't. Okay, if it could do full duplex, that, you know, would be wonderful.
Got it. Cool, thanks.
Okay, so working on this and being a hobbyist and thinking of all the discussions we've had in the past year, so I was thinking a little bit more about hobbyists. And, you know, the first question is, why does a hobbyist do what he does? Each person has his own answer, but in this particular case, looking at myself, I felt that the reasons were, first of all, making something work in the physical world. Okay, writing software that goes on the internet and reads web pages is also a bot. But it's not the same as having a little piece of metal walking around the house and tapping on doors and banging into bookcases. Second, it's an opportunity to learn a new technology in a fun way, where fun means a safe learning experience. Okay, your job is not on the line. There's no risk. It's a toy, you know, we like playing with stuff. It's something you can show people, you know, it's a conversation starter. Oh, look what I did. It gives you the opportunity to meet like-minded people. By like-minded people, I don't mean people who like robots. I mean people who might be like-minded to you, and that manifests in the fact that both of you like building robots, as opposed to talking about Jane Eyre. which is not bad, and I do that for somebody else. Self-realization, you're doing something. There's the issue of riding the wave. Right now, there's a wave of robotics taking over the world. And by having a hobby, which is robots, you can feel as if you're part of that wave and part of what's happening. And I don't know, do any of you have other reasons why you are doing this rover hobby?
Midlife crisis.
Okay, I was not going to say that.
Got to admit it, get it out of the way. But yeah, that setting aside midlife crisis, and apart from this is sort of on the more personal side. There's also this side of like, software eating everything, and it's finally gotten to this kind of hardware. So it's a very interesting sort of reset of everything I thought I learned when I was in grad school. So 1997 to 2003, this was like previous generation. And now like enough things have changed in enough places in the stack that it's a very interesting time to revisit and ask what has changed, what has not changed, what techniques still are usable and applicable, and what techniques basically need radical rethinking. So it's kind of like a good time to do almost refresher course, because now getting like version N+1 refresher basically. So that's been a big part for me, because it kind of helps on the consulting side as well, to the extent I work with companies doing this kind of thing, sort of updating my mental models of it. So that's been a more practical side for me. Yeah, I have a bunch of like clients that are like involved to various degrees in robotics.
For that, you have to stop being in robotics for 10 years.
Yeah, so it's kind of interesting, because I think technical management is a much more sort of future-proof discipline than technology itself, which is another way of saying that it's also much more bullshitty. So if you go from like hands-on engineering to managing engineering to consulting engineering managers, and this, by the way, it looks like it's turning into a chain of bullshit, but the people I've worked with are like competent and good. So even in the best case, though, you're kind of like a couple of levels of indirection away, and like, managing an engineering team hasn't changed as much as the technology of like low cost single board computers. So the low level stuff, I think, moves faster than the high level stuff. There's this, have you guys seen Stuart Brand's model of like shearing layers, I think it's called? So it's like an idea of like layers of things moving at different rates. So it's like sometimes it's fun to dip into a layer that's moving faster when you're from a slower moving layer. So that's partly how I think of it, because and all this personal stuff is very interesting too. And what Yasha calls new botics or new robotics, there's a lot of reasons to get into this particular hobby right now, apart from like general reasons to get into any particular hobby at any given time. But yeah, I'm curious to hear what got other people in as well.
There is also the opportunity. It's you said that implicitly, but about the ride the wave kind of thing, and the fact that we have a venue, we have a kind of I don't know. We all have other jobs to do to pay the bills, basically, and so we need to organize ourselves to have a venue where we can reserve time, basically, to do all that. Okay, so. Personally, I would say that without the weekly schedule to drive part of my time, that would remain a side project, basically.
I think in my case, I got into computing, I was programming when I was younger, but I got into computing for real in the late 90s and jumped into that as a profession. And at the time, it felt much more like a frontier than it does now. And I've always kept looking for new things to kind of get involved with and poked at a lot of different fields and so on. And robotics is the first thing in a long time that right now caught my feeling of sort of being more of a frontier. And I really enjoy that feeling. So I've managed to keep a little bit of that alive over the last 20 years as it gradually dwindled a little bit in the primary field of computing and regulation started to set in and things like that. But robotics feels like it's a new, even though robotics has been around for a long time, it still feels like there's a bit of a frontier edge to it. And there's a lot of unanswered things, and there's a lot of things that are possible, but technically possible, even if they're hard, but they're not being done yet. So it's got a lot of open space to explore, and that's why I really enjoy being a part of it.
Yeah, for me, I'm here just to have fun. That's the only goal for me. Like no other goal other than having fun, because I think I started robotics in 2006, and I did that for around 10 years. And then I was doing it mostly in academia, and then I quit academia, and then I didn't do robotics on a daily basis for around 5 years. So it was kind of a hobby. So if I would not have come in this group, I would be mostly doing the software stack. I would not be like playing with hardware as much as I'm doing right now. But yeah, but I've been doing this for quite some time, but not on the hardware level for around 5 years. So it's fun getting back and doing the things I used to do 5 years ago. So yeah, for me, this has been I've been doing this for a long time, and like doing it more and more, getting more time to do it is really makes me happy. That's it.
Yeah, I'll say that all these things here on the slide definitely resonate. But for me, chasing what's interesting and problems that are satisfying to solve was probably one of the most important things for I guess selecting this hobby. But I realized kind of in retrospect that it was also a bit of a path not taken exploration, because when I first went into school, my intention was to do more of a hardware software hybrid where using computers to interact with the world seemed super interesting, but I totally got sidetracked and went pure software and completely forgot about all of that. So coming back to it later was kind of interesting from that regard. But also just like, yeah, having the opportunity to chase whatever is interesting without having an explicit goal is fun. But also it means that I don't get as much done as I'm so like distracted by the new problem. Like got the 3D printer and I'm just like, well, that just ruined all my plans for the next couple of weeks, but now I've got new parts of the project to work on. Okay. But so yeah, the fact that doesn't really matter if I do that is awesome.
Okay. But it's not all fun and games. There's some pretty big challenges. First of all, there's a big range of designs to choose from. And design is a commitment. I mean, some of us can build a bot and then throw it away and then build another bot. But there's a lot of commitment. A lot of what you're doing depends on the specifics of your design. And it's also very complex. You have a lot of technologies that you have to deal with. There's hardware, there's software, there's mid-level hardware, there's low-level software. There's plastics, there's motors, there's metals, there's connectors, there's environmental protection. I could go on. There are a lot of parts. There are a lot of ways to fail. And by fail, I don't mean not provide the product that was ordered. I mean what I said earlier today, you know, moving forward requires moving forward on a wide front. Working in a team is much more difficult than in software. Okay, you can't pass a piece back and forth. It's an expensive hobby. And it's easy to damage the components you're working with. Again, I'm comparing it to software, which is super cheap. And you can't damage anything, you just pull it back out of your repo and there it is again. But rovers, as a particular type of robot hobby, have several advantages. You know, I was thinking about the question, we keep on talking about rovers, and we might have got into rovers because that is what you have on Mars. But you know that most robots are not rovers. Most of them sit on the table and weld or paint something. And I just saw one a few days ago. Again, it sits on the table and it does something. Rovers have some very interesting advantages for a hobbyist. First of all, it's very easy to measure success. Okay, the task is well defined. You have to get from A to B. We can measure things that you can't fudge. How long did it take you? How far did you go? Did you flip over? The substrate that you're operating on is always changing, okay? It's not a robot that's on your table and it lifts something up and the world always looks the same, except that maybe the red cube moved over a few inches and maybe the blue cube is rotated. Okay, once your rover starts moving, even if it's happening in your house, even if you have a carpet, the walls change, the bookcases, and if you're outside, it's completely different. The amount of complexity you have can be titrated very, very well. You can start at a very easy level, okay, just having the thing move. You can be very complex. You can add things like sensors, autonomy, functions, features, and you can do it at your own pace. Okay, if you compare it even to drones, okay, if you buy a hobby drone and now you want to add a sensor to it, that is very, very difficult. It might not take off. Where are you going to put the wires for the power? It's very easy to explain what you're doing to other people, even non-technical people, even incremental steps. Imagine you're building a robot which lifts up an item, rotates it, identifies it, and puts it down. And you've improved the algorithm so identification went up from 94% to 96%. That's not very exciting when you tell it to somebody. But I've managed to shave 2 seconds off my time to get from the door to my bedroom. Everybody can understand that. I bang into walls less, people can understand that. And last, the rover is on the ground. It's on the ground, so it's a big risk of falling down or catastrophic crashing into something or getting caught on a tree or doesn't exist. And you have a longer battery life compared to other moving things because you can just stop and be stopped. So I was complaining about not having 24/7, but I definitely have more than 40 seconds at a time. Okay, so all of these are advantages, which mean that if you want to go into robotics, actually the place to start is with a rover, because a rover can more easily fit where you are and gives you a easier way to grow in the direction that you want to grow and at the speed that you want to grow. So that naturally leads to the next question, which is how can the Yak Collective help this type of hobbyist? So I sort of a few things that we've talked about them. So first one is simply a knowledge center. We talked about summer school, repository for software. We already have software, and the minute people are comfortable with it being put out there, something that works, we can do it. Toolkits, meaning use this robot and that design and this software, and this is what you should expect to have. We can definitely provide inspiration, and we do it two ways. One is these show and tells, look what I did, and you can do it too. And the other one is success stories, which is basically maybe I should call it success journeys. Here's the journeys that I took. Here's what I did. You can walk in my footsteps, or you can decide that you're not walking in my footsteps. Either way, you're inspired to do something. I would like to focus on number 3. Let me skip to number 4 for a second. The Yak Collective could match up people that work on a project. I believe that originally Venkatesh had hoped that each build leader would have, let's call it, a few people working together with them on various components of the build. Okay, we're not there, but we could be there. It could start from having different people designing different components for 3D printing at whoever it is doing the building, and continue with software, which can definitely be distributed. And also providing manageable subtasks. If you want to get into the field, but you don't want to buy a robot, you just want to see what it's like, well, I could let you plan my robot for a few hours and see if you like it. You can write a module and see if you like writing modules for robots. You can suggest a new design for a suspension system and convince Venkatesh to swap it in his robot and see what happens. Okay, so you can have subtasks, and that's a gateway into the hobby. Okay, so let's talk for about number 3 for a minute. Framework. I just learned the framework about strategy, and I saw how having a good framework, even if it doesn't actually solve your problem, helps you arrange your thoughts in such a way that you can solve your problem. So, for example, we can define a test bed, the Mars garden, which we'll talk about in a minute, or benchmark tasks. And if you recall, it's easy to measure success, and we can measure things very well, that allow you to evaluate yourself and see if you're actually progressing at the speed and in the direction you want to do it. We can define standards of success. Okay, so the DARPA challenge is perhaps a too high a standard. Get from here to there 100 miles through varied terrain in less than 24 hours. But we can definitely have a whole range of standards. We can provide interoperability standards, which will allow the rovers to talk to each other and share things. And again, we define them. We do it on our 6 builds. And with any luck, other people will want to join in and also be interoperable with us. And we can talk about component standards, different components which can be shared between robots. Now I've seen quite a bit based on the previous calls we've had. I've seen software as a service components for robots. but they're not quite suitable for hobbyists. They're too, I don't know, heavy and sophisticated and not as much fun. So I'm thinking these are 4 different ways in which the Yak Collective and especially the Mars rover project can outreach to robot hobbyists and perhaps start a snowball growing. Anybody have other thoughts on ways the Yak Collective could help rover hobbyists?
I had I had one idea that was rolling around in my head the other day that I think kind of combines a couple of these, but in my own head, I started awarding myself badges for making progress along kind of certain areas of development to where I'm like, okay, I've got my intermediate embedded Arduino programming badge. That one's in the bag. So now I go over here to my 3D printer and I'm like, okay, I got beginning 3D printing, beginning modeling. Cool. What am I going to work on next? And kind of deciding if I want to go broad or if I want to go deep on one thing is a question I always have to be asking myself. And also, I think it comes to like number 4 there on teams, like matching people with complementary interests or complementary skills, or maybe the badge idea means that you're trying to produce a bunch of journalists and that makes teams harder. I don't know. But that's what I thought of.
Yeah, I'll add a +1 to the badge idea. I think it's a very sort of creative and imaginative way to do something that'll serve the same function as like boring organizational models. Like, you know, we've talked before about having like, we have these build teams, which are kind of like vertical integration projects. And you can think of like horizontal functional things like, you know, we have an electrical engineering or a software or embedded sub team or mechanical sub team. And that sounds very boring and the way a traditional engineering company is organized. But can you do something like that with a scheme of badges where a series of badges make you like a horizontal expert on embedded programming and another series of badges makes you a vertical expert on legged rovers, for example. So it I think gives you an interesting way to basically gamify the whole hobby. And that might be fun because I think lots of successful sort of hobby scenes do have an element of gamification in them. You don't want it to be too arbitrary or like the gamification becoming the end in itself. It should kind of be, I don't know, kind of light touch stuff so that the focus is still on the rover robotics. But I really like the badge idea. I think we should actually, once we're through this cycle, we should talk more about it and try to do it.
Do you guys know what an overall is? So in Finland, in university, we have a culture of wearing overalls, and the student, so each department of the university, whether humanities or engineering, like each, for example, mechanical engineering, electrical engineering, they all have their own guilds, and then the guilds have their own colored overalls, and you get patches. You can buy patches, and there are competitions for patches. And which, if you, for example, there is a patch for, okay, if you go and do some activity, then you get a patch from that guild for, and that patch. So there is a, like, people try to collect as many patches as possible during their 5 years of the university. So if you search, I'll put a link. So people sew this patches on their overalls for like 5 years, and then, and like, it's like a memory for them of their university life. So there are like special companies in Finland that makes patches, and each guild has the different kinds of patches, and for different activities, people make different patches. It's kind of fun activity.
That's interesting because during the previous question about why joining such kind of hobbyist project, many of us have answered with some form of fun. Okay, and what's interesting with this badge approach is that it's really an operational approach to fun. Okay, with gamification. And it makes me think about the system called Discourse. Maybe you've seen several projects using Discourse as a Q&A platform. And if I'm not mistaken, you can have a system of badges inside the Discourse, and I think you can configure it. So perhaps it can be one way to actually have a Q&A place where we can talk about different topics. It's a forum. Okay, Discourse basically is a forum technology with badges built into it, basically. But as long as we call that a Flare system, I'm okay.
If we can do that in Discord, that would be good, because otherwise you'll end up forking our conversation platform. But another place you can do the same thing virtually. I think we should have like a physical one, like an overall with actual cloth patches or badges or something. But virtually, I think our website is the natural place for it, since it's already got a member directory with member profile pages. And then that's the sort of natural place to put like digital badges for everybody. And then the physical ones can be on like some physical t-shirt or overall. I like the idea of overall. It'll make me feel more like a scientist.
What Anuraj said reminded me, my commander in the Air Force had a walking stick, not the kinds that people that can't walk use, but for people doing walking tours of Europe. And apparently in Austria, and I guess Bavaria and other parts nearby, each small town would give you a little badge to add to your walking stick if you walked through them. So he would go on walking tours and collect these badges on his walking stick. Now, it occurs to me that if we put together what Rhett described, which is really a skill voyage, but the rovers are actual rovers, we could have badges like 5-meter obstacle course, or avoided 4 cats. I don't know, whatever the badges are, but the badges could combine actual going from one place to another. And maybe the badges belong to the robot and not to the person. You know, you can say, I've built 2 5-badge robots. That might be more exciting than saying, look what badges I have.
I think we should have both. Like, you should have badges for the robots, but I think the value in having badges for the individuals is you can do like small components that contribute to multiple robots and may not be like, tied to a particular robot. And also, I think the sort of the big reason to do this is it creates an interesting social reinforcement, like, dopamine hit feedback loop. And I think the rate of earning badges that can go on human overalls will be much faster than the rate of earning badges that can go on the robot, because the robot is higher threshold. But I think we should do both, like make robots and humans equal level participants in the Yak Collective rover project, and both can earn badges.
A related concept would be mission patches for your rover accomplishing specific missions or something.
Yeah, this is definitely something we should, I'll put it in the agenda topic list to discuss when we do our next project management meeting. I like this, because I've been actually thinking in the back of my mind that we need a way to do more project management scaffolding, but traditional project management is boring. We don't want to end up like, bureaucracy in Google or some big company. So what's a fun way to do it? And I think this is the answer. Some version of this is the answer.
Yeah, just while it's in my mind at the moment, I think there's kind of a difference about learning the basic skill, where when you first encounter it, maybe for a badge, the problems we've been encountering on our rovers are of vastly different levels of complexity. Like, we'll run into some issues that it's really easy to fix in 15 minutes and just move on, and some things which can consume very significant amount of time to get any result at all, and long-term troubleshooting. So for someone learning something and achieving a badge, it seems like it would make sense to have something finite in there that has some relatively well understood characteristics in terms of how much time it's going to take for them and effort it's going to take for people to do that, as opposed to maybe the mission type badges where your rover is now encountering, the rover itself is encountering more complexity. So like our actual rovers are significantly complex, but maybe learning the individual technologies or skills involved in doing a particular thing can be made simple and then applied in the more complex scenario later. Does that kind of make sense as a model for kind of separating things out?
Yeah, I think that's, yes, we should do that. Like some version of that, we should do that. Yeah, like separate the complexity levels, give things for beginners to get into the thing, more experienced people to dive in and do more complex things, and then long range mission patches for people to earn over like a year or two. Like, there should be, it's interesting to have things you can earn in like an hour, things you can earn in a week, things that'll take you years. And of course, an ultimate badge that none of us will earn unless something actually goes to Mars, the Mars badge, right? So yeah, we should basically cover all time scales. And if you look at like well-designed, like badge-oriented games, they kind of have this logic. Like, have you guys played Bejeweled, the jewel matching like matrix type game? It's a very common genre. So it's like you basically match up. It's a grid of various gemstones, and you match up similar ones. And if you achieve various things, you end up with badges. So there's actually a badge gallery in your profile page. And as you play, you actually find out that certain badges are very easy to earn. Like some badge you'll earn in the first minute of your first ever game. Some badge will be extremely rare and you're likely to only get it after like 100 games. Like, a supernova badge is like when you match up 6 gems or something. So you kind of want to borrow that logic, like give people loops and achievements at all time horizons. So I think that definitely is, there's interesting design problems here, and I think we can make a start on it. Like I think in September, when we talk about like doing the event later in fall, we should sort of introduce this badging scheme when we sort of invite more people in the next cohort. So hopefully next year we'll have quite a few more people, and this badge scheme might be perfect for that.
Okay, so I promised to talk a little bit about the test bed, so we're running out of time. So I'm giving a suggestion for high level specification. Okay, so this test bed Mars garden should have a given size, and we have to decide if we have a size that fits in apartments, only a size that fits in gardens. It should be built out of standard materials, pea gravel, rocks, marbles, empty milk cartons, whatever they might be. It should be easy for the person doing it to verify that he's complying with the definition of the Mars garden. There should be parametrically different designs for wheels, legs, the size, type of suspension. Okay, but it's important that it be parametric. Somebody, not me, should make it have a stunning visual design so that it won't get taken apart. But the way Collisters have herb gardens with winding paths and same kind of thing. We should also define where you put cameras or other sensors so you can have automated scoring. Okay, it's nice if you have a camera which can detect that your rover got from place A to place B, what path it did, and so on. And a series of benchmarks, or maybe it's a tree. You can go down this path or down that path, I guess, in order to earn badges. So I'm definitely not making any particular suggestion, but I'm thinking that we could define something like this. I didn't write how long it takes to build it, but let's say that you can put together in an afternoon for $100 worth of materials, and which will allow you to participate. And you know, you're participating and you know that 100 other people in the world have a test bed exactly like yours. So if we manage to define a useful test bed, I think this could be very helpful to people who are into rovers and they want to know that they're incrementally improving what they're doing. Okay, that's all, folks.
Great. That was a great update.
Maier, just a very quick question. You mentioned that the Arduino version of the Spider could potentially solve several of the problems faced on the logging part. Isn't it then a good option then to buy the Arduino version? I mean, so that we can focus on the actual logging and the actual piece that where we think we can contribute, basically.
So when you asked that question, what went through my mind is we take the Arduino version and we put a Raspberry Pi or Jetson on top of it. And the Raspberry Pi pretend to be a computer that's talking with the board. Maybe.
I know we'll talk about that at some other point. It's just that following, you know, the reasoning you presented about whether you buy or whether you build, basically. Okay, so
Yes,
just
yes.
that. Yeah. Okay. Thank you.
Interesting thought. I wonder.
Well,
I wonder if
it's
they
a
use the same board. That's all.
yeah, I don't know that. It's money against time, basically, and to select so what we focus on. When you say we as an individual, basically. Yeah. Okay. Thank you.
Okay, so I'll pause the recording. End it.